Okay.
All right. Yeah. Welcome to the first Q&A session. So raise your hand and we'll start taking questions.
Yeah.
Yeah, great question. So the question is about what is a frame that came up in lecture and what does it mean and kind of what's the point of those? Frames are like a memory where the computer or the interpreter is keeping track of what names mean. So it's up to you in the course of the program what names are assigned to what values. Is x12 or is x14? And the frame is there just to keep track of that. Now, in different frames, the same name can mean different things. And that is one of the key things to learn here, is that when you're executing code that's inside the body of a function, x might mean one thing, and then outside the body of that function, x might mean something else. So let me show you kind of the simplest example of that, and you can let me know if that answers your question. So if we say something like x equals 12, and then we define a function of y, which sets x equal to 3. And this prints out x. And then after we call this on 7, we print out x. We have two lines that are identical, print x, but they'll print different things. We assign x to 12 in the global frame. We create a function. That function hasn't been called yet, so we don't have any additional frames yet. The additional frame comes when we call f. Regardless of what we call it on, we're going to create a new frame, an f frame. So a frame is one of these boxes. And here, y is associated with 7, or bound to 7. But the assignment statement x equals 3 will bind x to 3 in the current frame, which is this local frame. So when we print x here, it prints out 3. Now we're done executing the body of f. It's time to print out x again. But when you finish executing the body, you return back to the frame you were in before. So now we're back in the global frame where x equals 12. If we print x in this context, x is 12. So the whole point is that in different contexts, different name, or the same name might mean different things. And frames are the mechanism by which this is tracked inside the Python interpreter. If you know how that works, then you can write code that takes advantage of it. So you can have x mean one thing inside of f and a different thing outside of f.
Let me add one more thing too, is if imagine a world where this was not true. So what you should know about coding is we tend to reuse the same variable names. Like we use x and y a lot. We use I, j, and k a lot. We use f a lot. And imagine a world where that wasn't true. You would run out of variable names very fast, first of all. And imagine now you've got thousands of lines of code, and somebody wrote one function and somebody else wrote another function, and they used x and you used x, but you don't know that they used it. Well, then there'd be no way of keeping track of variables. And you'd constantly be colliding. Somebody's asking, is a frame called the scope? And the answer is yes. You can think about that. You have the scope of evaluation. Where are you evaluating this? It's within the frame that you see up on the screen right now. And right now there's only two frames. There's a global frame and then the function call frame. Eventually you'll see that they can be nested a little bit deeper. When you call a function, a frame comes out, local variables are evaluated within that. When you exit the function, that is done. You are done with those variables. You return back to the global frame. By the way, that means that the global frame is very powerful because any variable in that global frame has only one name, right? So there's only one x in the global variable. Yeah. Sorry, in the global frame. And so we'll talk probably later on about global variables, that they are considered to be dangerous when you have a lot of code because they start to annihilate each other. Yeah. Sorry, I'm going to try to keep track of some of the chat questions.
Yeah, so just to follow up on this, and then we'll move on. I'd say like the beauty of this design is that, let's say I want to print x, y, and z. Anything that's defined here or inside here isn't going to be affected by stuff outside. So you can kind of just stare at this function to decide what's going to happen with x. Once you see that x is defined within here, you kind of don't care what it was before. And that means you can sort of focus on what you care about. At the same time, anything that's not defined within here can still be accessed. So I'll show you that since the global frame has an x and a z, if I've used X in here, then the global X doesn't matter anymore. But the global Z does matter because I didn't come up with a local Z. There's no Z inside this frame. And so I am able to print X and Y and Z. Oh, I shouldn't have used 7 twice, but we got this 3, this 7, and this 7 by accessing values that were in both the current frame and the global frame. So they're both accessible. In computer science terminology, you could say that all of X, Y, and Z are in scope, meaning they're in the current frame or they're in the global frame. But knowing where they are means you know what to look up, right? So you look up X by first looking in the local frame and then looking in the global. It's really, as you program more, you'll see this is quite a nice design in terms of letting you just focus on the names that you introduced and not worrying about anything else, unless you really want to refer to something in the global frame, and then you can. We forgot to repeat the next question, so here it is. The question was, what do you do if you want the local X to be the same as the global X?
Good. So if you wanted to use X, that global X, you would simply, if John deletes, thank you, John, if he deletes that line, then what happens when you call print XY inside of F? So the way it works, it says, what is X? Well, is it defined locally? And it starts in the local frame. It says, has the function F defined X for me? Yes? Great, use it. No? Well, go up one frame. Is it in the global frame? Yes? Great, use it. If it's not, what happens? What do you think happens if John deletes X equals 12 up there, and I said print X, Y, Z, what do you think would happen? That's exactly right. So it's not in the local frame, it's not in the global frame. I have no idea what X is, we're done, right? So it starts where the frame currently is, that's the function, looks for the variable. And somebody asked this in the chat room, is why doesn't it use the 12? And that's because there's an order, there is a precedence for the evaluation of the frames.
Though I think in this case, maybe you're trying to do something different. Maybe you want that global X, but you want to do something new to it. And that's fine. But then you have to give it a new name. So you could say A equals X. What this is going to do is create a name in the current frame, which has the same value as the global X. So it will be 12. And then you could do something with it. You could say B is A plus 1, and then you could print out A and B. So this is a common pattern for using something that's global, but you don't want to change the thing that's global. You just want to access it. So here, we access it by referring to it. We don't have to define it as anything. We just refer to it.
Yeah.
And now we have our own copy. We have a different name for it, A, but it's the same value as X was in the global frame. And so we could do something with that. Yeah, good question. The question is, what about environment diagrams? Like, how much should you know about them? I think it really is important to know what they mean. And so knowing what all the arrows mean and all the names mean and what parent means, which we haven't covered yet, but we will next week, is something you should learn in this class, because you need to be able to predict exactly what even a complicated program will do. And what happens with students is that for simple programs, you can always just kind of look at it and say like, oh, this adds 1 to things. It's very simple. You don't need an environment diagram. But as soon as something gets complicated with functions calling other functions, which are calling other functions, keeping track of that becomes kind of beyond the capacity of something that you can just do by staring at it. And so you make wrong predictions about what the program's going to do. That is a hindrance to being a programmer. So environment diagrams are a precise and correct way of describing what happens inside of a program. That's why we teach them. These are generated just by looking at the innards of the Python interpreter and displaying them to you. So this is like exactly what's going on inside the Python interpreter. And yeah, and you need to understand all of the mechanics if you want to predict the behavior of a Python program. So in that sense, you have to know all the details. Now, what about exams? Well, actually, yes, on exams, we used to just have people draw environment diagrams. Now, in the online world, that doesn't work quite as well. Usually what we do is draw an environment diagram and ask you, like, which piece of code would have generated this? And you still have to know the same thing. Like maybe you won't get tripped up by drawing your arrows with the wrong thickness, like that's not an issue anymore. But that was never really an issue. What is an issue is understanding what all the names and arrows and values mean and why they're there, so that you can understand how that corresponds to the execution of code. The next question was, do built-in functions like min and max create frames as well? Or do only user-defined functions create frames when you call them? Yeah, good question. With built-in functions like min and max, we don't really care how they work in order to be effective programmers. Now, you might care, you might be very interested, and I'll tell you, yes, there is the same notion of a frame, but we don't draw it because we're just trying to use abstraction. Min is something that takes the min, who cares how it does it? So we don't have to think about like what the mechanics are. We don't have to keep track of the frames. So in these environment diagrams, we only draw the frames for user-defined functions because those are the ones that we define, and therefore we have to understand how they work. So yeah, the short answer to the question is we only draw frames for user-defined functions, but they do exist. We just don't draw them for the built-in functions.
Yeah, but you're absolutely right, Sandra. The same thing is happening. If I had written my own min function, it would have a frame and have the local variables. But as John said, once you go down that road, the environment diagrams get really complicated because that function may call another function. And so anything that's built into Python, you just assume it does the right thing, and we don't worry about mapping all that out. Yeah.
The next question was, could there be more than one local frame? At any moment, so like things happen in an order. At any moment, there is a current frame. What happens if one function calls another function? Now we're in a different local frame, but that old one still exists. We're going to return to it when we're done, but there's still kind of only one current one. So let me show you just like a quick example of that. If we define f of x equals the result of calling g on x plus 1 and then adding 2 to that. And what's g anyway? Well, g is a function of y that returns y plus 3, let's say. Okay, so now we call f on 7. We have two different functions. Right now we still only have the global frame. We get one new local frame when we call f. In order for f to return, it needs to call g. So we can't return until we know what we're returning. And that involves calling g on x plus 1. So we call g on 8. When you call g on 8, you create a new frame with its formal parameter y bound to the argument 8. Now this is the local frame. I would call this the current frame, and these are both local frames, but there's only one that we're using right now. We're using this one for g, and we're going to keep using it until g returns. So we add 8 and 3 together to get 11. When you return back to whatever you were doing before. So now we're done with the g frame, but we have to go back into the f frame in order to finish what we were doing, which is that we were trying to return, but we didn't know what g of x plus 1 was. Well, now we do. It's 11. So we can add 2 to that. Now we're in a different current local frame, and we're ready to return from that, and then we're done. Okay, so somehow we're going to try to print the result of squaring 4, and in lecture, it turns out this actually works. Now, you would never write code like this.
No,
but the fact that it works is kind of interesting. So in the environment diagram, you enter here, and the question was kind of something about this. So I'll listen to the question, and then we'll keep going. Yeah, great question. So the question is, in lecture, I said that Square has a new frame in this environment. What's an environment? Is it just the frame, or is it something else? Well, here's where things get tricky, is that an environment, which is all the names that you can refer to, is actually a sequence of frames. Each box here is a frame. But all the names that you can refer to are not just here. They're in a sequence of frames that starts here and then goes to its parent, which is the global frame. So actually, the current environment includes both of these frames, but in an order, with the Square frame coming first and the global frame coming next. The reason we call this whole thing an environment is that it contains all the names to which we can refer. And we do care about the order because when you look up what a name means, for example, if it's time to mul square square, we have to look up the name mul, which we look first here, but there's no mul here. So then we look in the global frame, we find it's the function that multiplies. Okay, so we're going to multiply, but we can't multiply till we know what we're going to multiply. And now we need to figure out what square means. So then we look here first and we find square. So we use the number 4 without ever looking in the global frame. So the environment is the whole sequence of first F1 and then the global frame. These are 2 different frames. And the reason they're all part of the environment is that you could refer to names in all of them, but you can only refer to this square. You can't refer to that square because that square is shadowed by this square. And so we actually do multiply 4 and 4 together to get 16, and that's what gets printed out.
Let me emphasize, you should never, ever, ever, ever write code like this. I mean, it's a good pedagogical example because it sort of makes you really force you to think. But this is not something you would do. You would call you can get away with it, but you really want to pick clever and meaningful variable names and function names so that the user doesn't have to rack their brains trying to figure out what your code is doing. Yeah.
A student wanted clarification about whether order was important.
Yeah, so that's what we were saying earlier with the x's. If you have a local variable x and a global variable x, you start in the local frame. Is it there? Yes, great, use it. If it's not, push up into the global frame. If it's there, use it. If not, you have an error. And that's what John was distinguishing between the whole environment and then the frames that are embedded within that environment.
The next question was whether a frame is created when you call a function or when you define a function.
The local frame is defined when you call the function. The function definition is just, hey, here's a promise that when you call this thing, I will do this line of code. But it's not until you actually call the function, that the frame gets evaluated, the variables gets instantiated, and you start executing. That's right. So the function is defined by this whole 2 lines of def and then whatever. And that whole thing is kind of like one big statement. It all happens at once. And now square exists. You can see this is stepping through how many steps are in this program. Well, there was 1 step to import mul. There's 1 step just to define square. It happens all at once, even though it's 2 lines. And then there's 1 step to print 12. And you can see we never created a local frame because we never called square. The next question was about printing strings, which was covered in the supplementary videos that are linked from Piazza that come from Professor Farid's other course, 206A. These are not necessarily in scope for 61A, but will be eventually. So you could learn about it now, or you could wait and learn about it later. But anyway, here's the answer to that question about printing strings and combining strings. Yeah, so I think he's asking, John, that versus print hello number, comma 2.
Yeah.
Right. So that statement is printing 1 chunk of data, right? It's hello, number, space, and then converting 2 to a string. And then the hello number, comma 2, you can see does exactly the same thing because when you comma delimit your data, then it just prints them with spaces in between them. So you can get the same result in 2 ways. So in my version, I was sort of making, the reason I do that example, by the way, is I want you to start thinking about data types, that when you combine certain data types, you have to be careful sometimes, like, numbers can't be added to strings, but you absolutely can just comma delimit everything and get the same effective result. So the other thing John could have done here is he could have said print hello number, comma, end equals, quote, quote, which means don't put a new line. And then on the next line, print 2. Yeah, so there's a couple of ways. So that would have been, thank you, John, and then print 2. So what that does is the first print statement prints on the line, but then it doesn't bring you down to the next line, and then the next number comes in right there. And he just doesn't have a space after number, which is why. Yeah, so the questions about this slide and what's going on with A and how come it ends up being 2, which is a great question. Here, there's a case where Python could have been different. You could have imagined that what happens is, like, it figures out what B is, and then it figures out what A is, or something like that. But that's not how the language works. And you can't program effectively unless you know exactly how it works. So this is just a rule you need to memorize. And the rule is that when you see an assignment statement, you actually evaluate everything to the right of equals before any of the names change. So that means you add 1 and 2 together to get 3, and you figure out that B is 2. So the 2 values you're going to assign are 3 and 2.
before you ever start changing B and A. And then once you have the 3 and the 2, you assign those to B and A respectively, which means A comes out to 2 and B comes out to 3. You're right that it could have been different, but it's not. And so you can introduce bugs in your program by not knowing this fact about multiple assignment statements.
And that's true, Melissa, also of a single assignment statement. If I say B is equal to A plus B, I look at the right-hand side of that assignment operator, I evaluate it, I get a value, and then I shove that into the variable. And if you have multiple ones, you do everything on the right-hand side, and then you shove everything into the variable.
Yeah, great question. So is print kind of, when you call print, does the same process happen as if you were calling something else, like min? Meaning, do you first evaluate these operand expressions and then call the function, or is there a different story? And the answer is that it's the same. In fact, Python doesn't even really know that print is special until after it gets called, and it's not called until these two things happen. So if you get the min of 2 plus 3 in A versus the print 2 plus 3 in A, the story is very similar. What happens first is that you figure out you're going to print. You're going to print whatever print does on 5 and whatever A equals to. Here we don't have an A, but we could put one in. And then you call print on 5 and 12. So print doesn't actually know that it's printing 2 plus 3. It only knows that it's printing 5. And it doesn't know that it's printing A. It only knows that it's printing 12. Now the behavior is different, right? So when you print, you get print output. Whereas if you compute the min of something, you don't really get any output. You just compute a value. And as you rightly pointed out, this is, call this result 1 and this result 2. The result of printing is that you can't really do anything after you print. That print output appears, but the value that you get back is none. So there's nothing really you can do next. Whereas with a function like min, you get a return value, and so you could do something else with that. So like, it wouldn't make sense to write res1 plus 7 and try to print that out, because res1 is just none. You'll get an error. This would give you an error. Yeah. But you could use result 2 in order to do something. So that's the big difference between print versus most other functions, is that print's point is to do something, to print output, as opposed to give you back a value with which you could do something else later, like min gives you back the value 5, at which point you could do something with it, like add it to 7 to get another 12.
So the question is, do all functions by default return none? And the answer is yes. If you don't put a return statement, just like a print statement, it doesn't have an explicit return. It has the side effect that it shoves something onto your screen, but the default is none. That something does get returned if you don't, and I think you can see it on the screen right now. So it's as if there's an implicit return none at the end of every function, unless you replace that with return whatever you want to return.
Yeah, great question. So the question is, in this function value, what is being stored? Like, what is there? And the best way to think about it is that it's all the code of the function, so the body of the function, along with information about where that function was defined. So we'll talk about why this is important. It's important for scope. This is kind of the topic for next Wednesday's lecture. But there's really two pieces. So it's just the code plus where that function was defined, because that basically tells you what other names are in scope or available when you're executing that code. Yeah, great question. So the question is, in the Python interpreter, why is it the case that you don't have to print 24? You could just type 24 and it displays it for you. This is a convenience. It is not how all Python programs are run. Instead, it's only true of this, what's called interactive Python interpreter. Another more formal name for this is a read, eval, print loop. Basically, this lets you figure out what expressions evaluate to without having to go to the trouble of printing them all the time. And the rule is that if you write an expression, it will evaluate it and display the value, unless that value is none, in which case it doesn't display it. So there's this like one edge case where if the value is none, then it doesn't show you none. It just kind of doesn't show you anything at all. This is different from writing in a file. So if you write a Python program where the contents is just 24, and you run that, you will not see the 24. So the fact that it displays automatically is unique to this interactive interpreter, and it's not true of Python programs that are stored in files. So the interactive Python interpreter automatically displays the value of the whole expression that you type in. So if you type in 2 plus 3 plus 4, it will show you 9. It doesn't show you everything that happened along the way. So if I put a 12 in here and I returned 5, and then what I did was print f of 3, it displays 5, which is the result of calling f. F really did compute the number 12, but do nothing to it. But it's just kind of lost. It really did return the number 5, which is what we got displayed. But if I evaluate f of 3 plus 1, I don't see that 5 anymore. I only see the result of the whole thing. So that's the rule of this interactive Python interpreter, is that it evaluates this whole expression and shows you its one value. It doesn't show you everything intermediate along the way. If you want to see intermediate stuff along the way, then you have to explicitly print it out. If I print this out and I say z is 5, and I print out z, and I then return z, and now I call g of 3 plus 1, I'm going to see the 12, I'm going to see the 5, and I'm going to see the 6. The 6 is the value of this whole thing. Good question. So the question is, if you call a function and what happens? The slide says you create a new local frame, and that creates a new environment. Creating a new frame is not different from creating a new environment. Every time you create a new frame, that means you have a new environment that starts with that frame. Okay? So if we call f of 4 and we call g of 6, let me just give some vocabulary. We've created a function, another function, no frames yet. Here, in order to assign y to something, we have to call f on 4. So we look up what f is, and we create a new frame for that. By creating a new frame, we have also created a new environment. The frame has x. The environment has f, x, and f and g in it. You could refer to any of these, plus like min and max and whatever else is in the global frame that we don't normally show. Here, we're done with this frame. And now we go back to where we were, because that's what return does. It says go back to where you were. We assign y to the return value, which is 5. And then we create a new local frame, which means a new environment. So every local frame is the start of an environment that starts with that frame and has some other frames in it too. So far in this course, the only kinds of environments we've ever seen are a local frame followed by the global frame, or just the global frame alone. The question is, what does it mean to make a new environment? That means just to make a new frame. And that new frame is the first thing in a sequence of that frame followed by the global frame. Yeah, good question. So the question is, can you access a local variable in the global frame? And the answer is no. There's no way. Oh, sorry, we never called f. We should do that. Then it's more interesting. F on 7. So x is bound to 7, but when we leave that local frame and return back into the global frame, there's no way to access that x. It's gone. And so we get this error, x is not defined. But the way in which you move stuff from the local frame into the global frame is by returning it. And then now this expression, which is a global expression, has the value of the local x. You then have to decide what to do with that, like give it a global name, and then you have access to it. So here's how you move local stuff to the global frame, is you first return it, then you give it a name in the global frame, and now you can refer to it in the global frame.
That's a good way to think about it. When you're passing parameters, you're shoving things into that local frame by passing them as parameters. You also have access to all the global variables up top. And when you want something out, you have to explicitly send it out with a return statement, because everything that's done in that body gets annihilated when the function is done evaluating.
Great question. So the question is, what non-pure functions exist that aren't just print? There are really two different kinds that you'll see in this course. Ones that display things like print, but in like real programs, they also do other stuff like, actually making your printer work or making an internet connection to some other computer or something like that. So they're doing some kind of like external communication. The second kind that we'll see later are functions that change something about the current environment or some other environment. So not only do they compute a value, but they also like change some value somewhere else in the program. They make some like, if there's some like representation of a rectangle, they like change it to make it bigger. I haven't told you how to do that yet. That will come actually not for a few weeks. Basically everything that happens in the early part of this class is based on pure functions that their only job is to return a value. Print is a notable exception. But we'll get into the later part of the course when we talk about values and objects, where one function will end up changing something about some other value somewhere else. The next question was, could you ever have a non-pure function that returns something other than none? Yeah, great question. You could write a non-pure function that also returns something other than none, like it could print x and return 2. Because this prints, it is a non-pure function, but it also has a return value. So what makes something non-pure is not that it doesn't return or it only returns none. What makes it non-pure is that it does more than just return something. It also, for example, prints or changes something or something like that. A good question. So do environment diagrams get more complicated than the one on this screen? Yes, they certainly do. Most of that complication comes from topics next week when we talk about higher order functions on Wednesday and their environment diagrams on Friday. There are actually only so many rules that you have to learn. You have to learn how assignment statements work. We talked about that for today's lecture. You have to learn about how higher order functions work, which if you don't know what that is, that's fine. That's for next week. And you have to know how return works. But there aren't that many rules. And a longer program just uses the same rules over and over again. It is important that you know all the rules. Otherwise, it's hard to be an effective programmer if you can't like learn all the details of some part of something and then use them to get something done. But the fact that it looks daunting now is probably because there are some pieces you know and some pieces you don't know. And once you know them all, life becomes better. So in general, students perform very well on these kind of environment diagram based questions because they learn the rules. Now, they don't always learn it for midterm 1 because sometimes they just haven't done it yet. But by the time I ask the same questions on the midterm 2 and the final, everyone seems to get them right who's been really like focusing. So all you really have to do is kind of listen to lecture, go to discussion. And when you think of something that's like, oh, I don't know exactly how that works, then you have to go and you have to try it. And if you still don't understand how it works, then you have to ask a question. But there just aren't that many rules. You could learn them all, and then you're kind of guaranteed to get it right. A good question. So the question is about environment diagrams, and why is it the case that some names are bound via an arrow, and some things are bound via just like putting the number right there. So in particular, here, we don't have y with an arrow to 2. We just like put the 2 right there. And here we have z with an arrow to this other thing. A good way to think about it is this is just a shorthand. The really important thing about the meaning of this environment diagram is that you might have multiple names for the same thing. And we'll find out later in the course that if this thing can change, it's important to know whether you have 2 names for the same thing or whether you just have two names for two equal values. So it actually doesn't matter whether you have two names for the number 2 or you have two different number 2s. There's really only just one number 2. But it really does matter whether you have two names for the same function or whether you have two different functions. Why does that matter? We haven't gone over that yet, and it won't be relevant for several weeks, but it does eventually matter that there's like two different functions here. We created one every time we had a def statement, and this assignment doesn't create a new function. It just gives another name to the same function. Yeah, so that's the like distinction of why we put some stuff in this objects area, is that these are things that might change and therefore need or somehow like compound, and therefore we need to know whether there's two names for the same thing or not. The next question was, if you have one function and you call it multiple times, do you create a new frame every time you call that function, or just reuse the old frame?
Every time you call the function, it creates a new frame. And you can think of it as sort of, when it's done evaluating, it disappears. And then when you call it again, it comes back. Now, I think in the environment here, you'll see it get grayed out. What happens, John, when you call it over? Does it overwrite the previous one, or does it create a new one underneath it?
So in the environment diagram, you will get a new frame every time you call something. We leave the old ones in there just so you can see what happened before.
But they're essentially
in general,
gone.
they're kind of, sometimes they're gone completely. Like Python doesn't even keep track of them. And sometimes they're effectively gone in the sense that in order to refer to something later, you'd have to do some trickery, which we haven't taught you how to do yet. But basically, like, they were there, but now we're done with them. Once you return, in general, like, you don't need the frame anymore. We show it so that you can kind of keep a history of what happened. But every time you call F, you get a new frame. Yeah, great question. So can a function create other functions? That's exactly what we'll do next Wednesday. A function that creates another function is called a higher order function. And how you do it? Well, I'll let you either read ahead or wait for the videos. A good question. Are higher order functions somehow anonymous? Not necessarily. So there's a notion of an anonymous function and a notion of a higher order function, and they're different. They're orthogonal. You could have a higher order named function, you could have a higher order anonymous function, and any other combination that you want. You'll learn about that on either Wednesday or I think Friday. There's nothing in the read. The question is, are you required to do the readings? There's nothing in the readings that's not in the lecture. Students have said that the readings are helpful. There's a lot of stuff crammed into the lecture, and sometimes there are more examples in the readings. But it's not like there's going to be something that's only in the reading and it's not in the lecture, and therefore you can't know it unless you do the reading. So do the reading.
I would recommend you do the reading. I think, especially if you're pretty new to the topic, I think they're going to sort of touch on slightly different things. The big concepts are all there, but I think it's a good way of augmenting the lectures.
Okay, but will we be ever tested on something that's not in the lecture?
I believe the answer is no. Everything that we'll test you on, we do try to cover in the lecture.
All right.
Or in the discussion worksheet for a few topics that are only in discussion.
All right, guys, thanks for your patience. We are at 10:20 now, so I think we're going to call it a day. For those of you who want to come to the 2 o'clock AMA, ask us anything. That can be about the class. It could be about computer science as a field. It can be about the major here. It could be about just about anything within bounds, obviously. And we're just going to be hanging around for about an hour or so and just talking. So hope to see you then. I think that there's a webinar link on the course website that you can join.